We'll go ahead and get started. What we're going to discuss today is referred to as classification and regression trees, or CART for short. So in linear regression, or general linear model is a continuous outcome, y in this case, and then we have an equation that involves the predictor variables or variables in the equation that we think are affecting the outcome. And then the betas are the regression coefficients that indicate how the independent variables are related to the dependent variables. In the generalized linear model, in this case, what I have here is binary logistic regression. We have the same sort of formula on the right-hand side, but what we're modeling is the log of the probability of the outcome divided by 1 minus the probability of the outcome. And so in either case, what we're going to do is develop a mathematical model by either maximizing the likelihood function or, in the case of linear regression, by least squares. And so what we want to do is come up with the model that best fits the data. And if we include all the predictor variables that we have, then that gives us the best fitting model. However, the model might be too large or too big to be meaningful. And so we have ways of then determining whether we can get by with a smaller model or not. So in tree-based models, what we're going to do, rather than develop a mathematical model, we're going to do what's called recursive partitioning. And so it's going to take the data and basically partition into binary splits. And so the procedure is to take the variable, the independent variable that will give us the largest difference in our outcome variable. So whether that be, say, age or race, sex, whatever it might be. And then we're going to continue partitioning the data into binary splits that include other variables, or it may also include variables that have been used once before in a different split. And so this is, in a sense, we can kind of look at tree-based models as exploratory, but we can also use it to actually develop a model. And perhaps one of the more useful tree-based modeling is to uncover structure in multivariate data, particularly if we have a lot of predictor variables. And so if our outcome is binary, then we refer to it as tree classification. If the outcome is continuous, then we refer to that as tree regression. So there are a number of advantages to CART. It's relatively straightforward to interpret. It also captures complex relationships and interactions among predictors. And it does that automatically in the recursive partitioning. If you have interactions in a linear regression or in binary regression, logistic regression, you have to include those interactions in the model. But in CART, they'll show up automatically. And so continuous variables don't have to be categorized. In fact, it's best to leave them as continuous. And then categorical predictors don't have to be collapsed or dummy coded, whatever, however they're identified in the data, you can just use that particular notation or however they're coded. And then also another really big advantage is that you don't have to worry about missing values. Well, in the sense that they're not going to be excluded from the model. And missing values take on another category in the analysis. And so if you have missing values, they're going to be included in the model. So when we grow a tree, then initially we're sort of like linear regression. We're going to enter all the variables in our for the initial model. And so this is going to give us the best prediction. So if we have a large number of variables, we have 50 variables that we're putting in the initial model. It is going to use all of them, although there is a caveat to that, which I'll explain later on in an example. And so there's two statistics that we're going to get that are going to tell us how well our model does. And that's the residual deviance. This is analogous to regression error variance. And then the misclassification error rate. We can also, from our tree, calculate other statistics that would be of interest or may be of interest. We can calculate sensitivity and specificity, and we can calculate an AUC, the area under the receiver operating characteristic curve. So this is what a tree is going to look like. And the root of the tree, which is actually, when we graph it, is going to be on top. And then we're going to then see the recursive partitioning take place. So in this example, our outcome is 40%, 40 out of 100, let's say, just for example here. And so the splits are going to result in what we call nodes. And there's two different kinds, just a regular node and then a terminal node. That means there's no further splits after the terminal node. So in this example, our first split is with age less than 65 or age greater than 65. And you can see the age greater than 65, there's a higher rate of a higher rate of the outcome. And so there's no, after age greater than 65, that split, there's no further splits. And so that's a terminal node. And the other node, age less than 65, then we have another split that ends in two terminal nodes, male and female. And so we can see the differences there. So at age greater than 65, the rate of the outcome is 75% compared with 17% for age less than 65. And then for sex, males versus females, it's 27% versus 7%. And so this is what a tree is going to look like when we run the analysis. But usually the model, the initial model, is going to be too complex. In other words, there's going to be too many nodes, too many terminal nodes to really make it useful. So what we're going to do, as you would with a regular tree, is we're going to prune it. And what we mean by that is we're essentially going to reduce the number of terminal nodes. And we prune from the bottom up. And of course, as you would guess or know, that the prune tree is going to be less accurate. And just like in regular linear regression, we can take out some of the variables but our model is going to be less accurate in predicting the outcome. So we have what is basically going to be tension in our model is we want to trade off between complexity and cost referring to how accurate our model is. And so just like in linear regression, we want to keep the prediction error within some limit of the smallest prediction errors, which is going to be given going to be our initial tree. So probably the best way to do this is to illustrate trees is to do an actually example. And so I have several examples here. So the first one is from the American College of Cardiology database, NCDR. And so this database consists of over 275,000 PCI patients, percutaneous coronary intervention patients. And so in this registry, there are 301 different sites that contribute data to it. They would have a quarterly report that goes to all the sites. And so in this version, although this is an older version, so there might be more by now, but we have 143 variables that are demographic, clinical, procedural variables that we want to use as potential predictors of the outcome. And so in the analysis, there were actually two primary outcomes that we were interested in hospital mortality and unplanned bypass surgery. I'm just going to focus on the in-hospital mortality. So in the database, there's three different patient groups. And so we're going to do, or what we did is a tree for each group. And so the first group is acute myocardial infarction with elevated ST segment, and then acute MI with non-elevated ST segment, and then non-acute myocardial infarction. And you can see that in this case, it's in hospital mortality, that the rate is highest with the ST segment and actually fairly small with the non-acute MI. So we're going to do a tree for each patient group and see what the tree looks like for each group. And so for most of them, there are 28 risk factors or 28 variables that we want to use as predictors of in-hospital mortality. And you can see that a lot of these, in fact, most of them are dichotomous variables. They're just yes, no. So if we were doing logistic regression, the yes would be coded as 1 and the no is 0. But in tree, it doesn't matter. They can either be 1s or 0s or Y or N. And then we have some that have more than 2 categories, like smoking history. And then there's a few that are continuous, actually just 2. So we have number 26 and 28 there, as well as ejection fraction can be looked at as continuous. That's age and BMI. And so we're going to enter those as continuous variables. So in terms of missing data, there's complete data except for BMI and ejection fraction. The missing BMI values are the number of missing values is fairly small, only about 2%. However, for ejection fraction, we have a fairly large number of missing values, 30% in this case. And that's because ejection fraction is not a variable that's missing at random. it's a physician decision as to whether ejection fraction is measured in a particular patient. So in the tree analysis, though, we're going to the missing data is going to just be another factor, just missing. If we when we did the logistic regression for this, then we did actually 3 different analyses. We did a complete case analysis. Then we did another analysis that include all the patients, but it would exclude anybody who had a missing value on any one of the predictor variables. And then we did an analysis where we imputed the missing data. So this is the program syntax. This is in S+, although this would probably work in R as well. The one thing that I want to point out here is that we're going to tell the tree function how many patients we want at any particular cut. And so in this case, we're going to say that if a cut involves less than 100 patients, don't make the cut. And so then we're going to get a summary output. We're going to plot the tree, which is actually what we want to see because that's what makes it understandable, interpretable. And then we're going to prune the tree. And when we do this, then the K variable is a pruning factor. That is how severely do we want to trim the tree. So in our acute MI patients, there's 39,000, and then the demographics of it. And then the death rate is almost 5%. So in the initial model, we're going to include all 28 risk factors. We end up with 145 terminal nodes, which is a lot. And our misclassification error rate is 4.5%. So with all the risk factors in there and 145 terminal nodes, this is the best we can do as far as misclassification, or have that as small as possible. And so we then also get a graph of the cost complexity. And so what this does is it plots the deviance against the tree size, how many terminal nodes we want. And then at the top there is our cost complexity variable K, which we can increase or decrease, and we'll come up with our optimal tree. And so you can see that what happens here, if K is really large, then the size of the tree is fairly small. But as you decrease the complexity factor, then the size of the tree increases as the deviance also decreases. So in pruning the tree, as we come up with 4 risk factors. And we have reduced it from 145 terminal nodes to 8. And these 4 risk factors are shock at PCI, ejection fraction, age, and history of congestive heart failure. And so with just 8 terminal nodes, our misclassification error rate is 4.8%. And if you remember, our error rate with all risk factors included was 4.5%. So our increase in the error rate here is pretty minimal, that we would not be we would be okay in going with just 8 terminal nodes as far as the misclassification error rate. And so this is what the tree looks like, would look like. And so as you might expect, the initial variable that has the greatest separation is shock. And so patients experiencing shock at PCI, the in-hospital death rate is almost 29%, compared to 2.5% for no shock. Then we get further nodes with over on the right side with shock at PCI. So the ejection fraction either greater than 40% or less than 40% or missing. So those that have an ejection who experience shock and have an ejection fraction less than 40 or are missing the ejection fraction, the death rate goes up to 33.7%. For those experiencing shock but have an ejection fraction greater than 40%, then the death rate is a little less than 15%. And then for those that have an ejection fraction less than 40 or are missing, we have another split at age, involving age, and age at 59, less than 59, and greater than 59. And so you can see that those greater than age 59 have a 39% death rate compared to 22.5% for those less than 59. So you can see that our initial variable of shock at PCI had nearly 29% death rate, but if we include ejection fraction less than 40 and age greater than 59, then that goes up to 39%. On the other side, where we have the no shock patients that have only a 2.5% death rate, we have another division or another split involving age, but you can see that the age split is different from those with shock. It's at 72. And so those greater than 72 have a 6.5% death rate compared to only 1.4% for those less than 72. And then, interestingly, which tells us something about the what we might want to do as far as if we did a logistic regression, an interaction that we might want to include is ejection fraction. And so for those age greater than 72, if they have an ejection fraction less than 40 or missing, the death rate is nearly 9% compared to a little over 3.5% for those greater than 40. And then for the age less than 72, we also have another split with ejection fraction, but it's the same as the splits in the other branches, so to speak, at 40%, greater than 40% versus less than 40% or missing. And so for those less than 72, then the death rate is 2.3%. And then our final split is at congestive heart failure, where if they have ejection fraction less than 40 or missing, and they have congestive heart failure, then the death rate goes up to 6.7%. So you can see that what we mean here by recursive partitioning, that we make the splits based on those that will give us the biggest separation between patient variables that give the biggest separation between patients. And so if we were to do like stepwise regression, regular stepwise logistic regression, we would probably get shock as our first variable that enters into the equation. But we see that we have, by doing a tree, we can see that the impact of other variables in the equation. So that gives us perhaps a fuller picture than regular regression would. And so you remember that we set our minimum cutoff number of subjects at 100, and so that's the case in every split here, that we're going to have at least 100. We actually have over 100 patients in each split. So this is just a table then of the terminal node mortality rates in the 95% confidence interval. And so you can see our largest mortality rate there is age, or is shock, ejection fraction less than 40%, and age greater than 59%, and then so on through the different terminal nodes. Okay, I'll kind of go fairly fast through the other groups here. So we have acute MI with non-elevated ST segment, and in this case, the in-hospital death rate is 2.2%. And so one of the risk factors that we didn't, or wouldn't have been included in this one, is previous valve surgery. So we come up, if we use all the 27 risk factors, we have 174 terminal nodes and a misclassification error rate of 2.1%. So that's the best we could do as far as misclassification error. And so here's our cost complexity graph again. And so in reducing the size of the tree to make it more manageable, again, we come up with 4 risk factors: shock, age, the New York Heart Association classification, and history of renal failure. And this tree has 6 terminal nodes, and the misclassification rate is now only 2.2% compared to 2.1% with the entire set of variables. And so here is the tree. And so again, you can see that shock is the primary driver of in-hospital death. And then we have a split for those at shock at age. In this case, age greater than 72, less than 72. For those with no shock, there's a split at age, but this time the split is at 69. And then age less than 69 has a split with renal failure, which is yes or no. And then age greater than 69 makes a difference depending on your New York Heart Association classification. And then, so this is again just a table of the mortality rates and 95% confidence intervals for each terminal or terminal node. So, and then finally, we have the non-acute patients. And so the in-hospital death rate is really small here. It's actually less than 0.5%. And so we include all 28 risk factors. In the initial model, we get 162 terminal nodes, and our misclassification error rate is really just about the same, or is a little less than 0.5%. And so looking at our cost complexity graph, and then we come up again with 4 risk factors: shock, the New York classification, and non-elective PCI. And we come up with 5 terminal nodes, and you can see that the misclassification rate is really small, hardly larger than our initial one. And so this is what the tree looks like with our first split, again with shock. So obviously for either or any one of the three patient populations. Shock is the primary driver of in-hospital mortality. And so in this case, those with shock there's no, it's a terminal node in of itself. There's none others. With the no shock, then we get a split based on the New York classification, New York hard classification, and then age at 65. And then for those greater than 65, there's another split depending on whether you have elective or non-elective PCI. So the mortality rates, again, they're not, obviously, as I mentioned, shock is the primary driver of in-hospital mortality for all of these patient populations. So I want to do one more example here that's a little bit different, but this is looking at parameters that predict nipple involvement in breast cancer. And so this is a retrospective chart review. The outcome is dichotomous, either yes or no. And then we have the predictors: race, age, tumor location, tumor size, grade, stage, etc. And so in this case, as before, we are going to do a logistic regression, which is, I think, was the analysis that was published. And then I did tree classification to see how it compared to the logistic regression. So we have a total of 103 total patients that have known outcome. 54 were positive for nipple involvement. But in this data set, we have a lot of missing data. For example, S phase has 83% missing. So we had to take this into consideration in doing the analysis. There were only about half of them had complete data for all of the predictors in univariate analysis. So again, what we did is we do a complete case analysis that includes just those that have data for all the variables. Then we do an analysis that includes all the patients, but the analysis will exclude those that are missing one or more of the variables, and then we imputed the missing data. So here's what the data set looks like. So there's race, age, location. Now I forget what U and O and I stand for. O is overlap, but there's different. I think there were 6 different categories for location. Then we have we have grade, stage, the size of the tumor, and then the outcome, which would be yes or no. And then we have node status, which is either positive or negative. So in doing the logistic regression, we come up with 3 variables that predict nipple involvement: stage greater than 3, location O or C, and then grade greater than 3. And so you can see the odds ratios that we get for each analysis, the complete case, those involving all patients, and those then with the imputed data. And so they're fairly consistent as far as the odds ratios go, regardless of whether you do a complete case analysis or you end up imputing all the missing data. So we're going to then do the tree classification to compare our results with this, but we're going to just do the complete case analysis. And in this case, we're going to set our minimum node size to 10. In the other, we had tens of thousands of patients. Here we only have 400. So our minimum node size is going to be 10. And so here is the first analysis with all the variables in it. with 6 of the variables in it. And so you can see what this, the output gives us here, that the variables actually used in the tree construction. So in this case, all 6 are used: stage, location, size, age, grade, and node status. And we end up with 17 terminal nodes. And then our statistics that we want to look at here are residual mean deviance, 0.35 in this case, and our misclassification error rate is about 7.5%. Those are the best statistics we can get for the error involved in this model. So then, well, if we actually did the tree, we'd have 17 terminal nodes. I haven't labeled them all because it was too time consuming to do so. But you'd see we have a tree that is probably not really useful because it has so many terminal nodes. And so what we're going to do is we're going to prune the tree to reduce the number of terminal nodes. And so using a cost complexity factor of 2, up here k equals 2, we still have the 6 variables, but we've only reduced the number of terminal nodes to 14. And so our deviance and our misclassification error rate don't change. In fact, the error rate or the misclassification doesn't change at all, I don't think. Yeah. So that doesn't really help us all. We still have too many nodes, terminal nodes. So we're going to prune again, and this time we're going to double our cost complexity factor, factor of 4. And now we come up with only 3 variables that are used: stage, location, and age. And we come up with 6 terminal nodes. Notice now that our mean residual deviance increases a fair amount, but our misclassification error rate is still the same. And so we might want to see if we can prune it further. This is just the output that we get with the stage age breakdown. As I say, this is better interpreted by looking at the tree. So in this case, our primary variable here is stage 1 to 3 A and versus stage 3 B or 4. And so you can see that the for stage 3 B or stage 4, our nipple involvement rate is 57% compared with only 6% for those with less than stage 3B. And so then those that the 57% with stage 3B or higher have another variable that splits it further, and that's with location overlap versus others. And so you can see that those that have overlap, the rate is 80% compared to only 31% with others as far as location. And then those that have stage less than 3B, we have another split in the tree, or partition in the tree, with location, this being central versus others. And the central location ends up with a rate of 38% versus others, which is only 4%. But then others has a stage, another stage partition, this time stage 1 and 2, and then stage 2A to 3A. And again, we have another partition with the lower stage, stages 1 and 2, at age 70. And so we can then reduce this down to where our at least our misclassification error rate doesn't change. Then if we were to prune it again, and we come up with only two variables, stage and location, we only get 4 terminal nodes, but now our residual deviance is quite a bit higher, but our misclassification error rate is still the same. And so if we go with just the 4 terminal nodes, again, we have stage as being the primary driver of nipple involvement, and then the others are location, overlap versus others, and central versus others. And so we'd have to kind of decide whether we want to go with this more simple tree or the one before it, where our misclassification error rate doesn't change, and although our residual mean deviance does. Probably we would go, at least in my mind, I would go with the simpler one, because the misclassification error rate isn't changing, and what that says is that stage is the primary driver, regardless of what other variables might be included. Okay, I want to end up with just an example. This is not actually from real data, I just made it up. But if we have a continuous outcome, then it partitions the continuous or partitions on a variable that has the largest difference as far as the continuous outcome is concerned. And then just as in the classification we continue partitioning with binary splits of predictor variables. And so now, though, what our statistic of interest is going to be the mean of the outcome at the terminal nodes, or we can also look at the distribution of the outcome at terminal nodes. But we get the same statistics as we do in the classification tree, or I'm sorry, yeah, in the classification tree versus in this case, what we're doing is a regression tree. So what we have here is just like a made-up example where we're looking at systolic blood pressure. And so I'd have 1,000 patients, and the blood pressure ranges from 83 to 215. And so our first split then comes with age, age at 72, greater than 70 or equal to 72 versus age less than 72. At the age greater than 72, we have another partition, whether they smoke or not, which is just a yes or no. And then so the number at the bottom of those terminal nodes, the yes or no for smoker, is the mean blood pressure for each of those two categories, smoker or not. And as I mentioned, we might also want to look at the distribution of those as well. And then for less than 72, we might have a division based on sex, male or female. And again, at the bottom of the terminal nodes, we have the mean blood pressure for each group. So that's how the analysis of a continuous variable differs from the classification or looking at a categorical variable. So just in summary, then, the tree models are really a great way to look at risk factor analysis that will give us all the risk factors that might be involved in predicting the outcome, whether it be a dichotomous outcome or a continuous outcome. And then, as I mentioned before, it will automatically give us insight into interactions between two or more variables, whereas in regular regression, we would have to either guess which ones might interact or have some idea beforehand, because we would need to include the interaction terms in the linear model. But it also gives us insight into how to categorize different categorical variables, or gives us ideas for cutoffs for continuous variables. So again, interpretation sort of, or actually really depends on how complex the tree is. And as we've seen, if you have a lot of variables, you can get a lot of terminal nodes, which makes interpretation really difficult. So that's why we prune the tree, we cut it down and see how good a model we can get with a smaller tree. And then finally, what you probably want to do if you had a big enough sample size, is cross-validate. So in other words, you might want to say, randomize your patient population into two groups, or maybe three or more. It doesn't, but you would run the model, develop the model on one group, and then you would use that same model to see how well it does on the second group, and that's sort of the same thing we do we can do in regular regression. So I'll end there. I've got a few references, a couple of references, and then I want to mention just in R, the routines are tree and R part, which R's part is recursive partitioning. I'm not sure about Python, but I would assume you could probably do that in Python. In some of the other packages, I'm not sure about SAS, but I know in Stata, that's not a variable or a routine that's available. I believe another major package that does have that is SPSS, but I'm not at all familiar with that. So I will end there and open it up to any questions that you might have about tree models.